Welcome back to Logic, Language and Information. In this lesson, we'll look at the precise construction rules for truth tables for the easy connectives, negation, conjunction and disjunction. In the following lesson, we'll return to the other two trickier connectives, the conditional and the biconditional. To begin with, recall that propositions are the sort of things that are true or false. By convention, we're using the symbol 1 to denote true and the symbol 0 to denote false. To see how this works for negation, suppose that a proposition A is true. In the table, this is denoted by a 1 in the column under A. Then, since we cannot have both A and not A true at the same time, at least not in classical two-valued binary logic, then it must be the case that not A is false. So we write a 0 in the bottom row. Conversely, if a proposition A is false, then not A must be true. Thus, as an input-output operation, negation inverts or flips 1s to 0s and 0s to 1s. This is called a truth table for the formula not A. It shows how the truth or falsity of not A depends on the truth or falsity of A itself. For the first of the binary connectives, let's look at conjunction. A conjunction is true exactly when both of the conjuncts are true and false in all other circumstances. In the table, we have both A and B true in the last row, giving us a 1 for the conjunction A and B. While in the other three rows, where at least one of A or B is false, we will get the conjunction evaluating to 0 or false. Notice that if we reverse the order and look at the truth table for B and A, then we get exactly the same pattern. 1 or true when both of the conjuncts are true, and 0 in the other three rows. What this tells us is that the operation of conjunction is commutative. The order doesn't matter, in the same way that addition is commutative. 3 plus 4 is the same as 4 plus 3. Also note that in the formal definition of the formal language, according to the strict rules, if A and B are formulas, then the conjunction is written parentheses A and close parentheses, surrounded by the parentheses. From this point onwards in the subject, we're going to allow the convention of dropping outermost parentheses when they are not needed to clarify or disambiguate. In all other circumstances, when parentheses are not outermost, we will insist on keeping them, since they definitely are needed to disambiguate the formula. Next, we have the dual, in a very precise sense, of conjunction, which is disjunction. A disjunction is true exactly when at least one of the disjuncts is true. And this is the inclusive sense of disjunction. In the truth table for A or B, if A is 0 and B is 1, then we get a 1. And likewise, if A is 1 and B is 0, then we get a 1. And if both A and B are 1, then we also have a 1 for the disjunction. So it's the only case in which the disjunction A or B is false, is 0, is when both of the disjuncts are 0. And it's 1 for all other rows. See how the pattern is dual to conjunction. Only the first row for the disjunction is false, where both disjuncts are false, and all the other rows give true, while for conjunction, only the last row is true, where both conjuncts are true and all others are false. Again, notice the order doesn't matter, so B or A will have the same pattern of truth table as A or B. Like conjunction, disjunction is commutative. Here's an exercise for you to test your understanding of truth tables. Suppose we have a new connective called star, where we want A star B to mean neither A nor B is true. Your job here is to complete the truth table for the star connective. Mark the rows of the truth table in which you think A star B should be true. How did you go? If you have questions or comments, take a look first at the course notes and then head to the discussion boards to follow things up. Based on the truth table construction rules we've seen so far for negation, conjunction and disjunction, we can already put these into practice and see how to build up a truth table for a complex formula using these connectives. The key is to start from the innermost atomic propositions and work outwards. So, suppose we have the formula not P and not Q. This formula asserts it is not the case that both P is false and Q is false, or equivalently, not neither P nor Q. We're going to start by writing out the formula with lots of space in between the symbols, and on the left-hand side of the table we write out the atomic propositions that occur in the formula. Here, just P and Q. To begin, evaluation at level 0 is easy. We just copy the column from under the atomic proposition P and write it again under each occurrence of P in the complex formula. Likewise, for each occurrence of Q in the complex formula, we take the column under Q and copy it. At the next, first level of evaluation, we're going to work on the connectives closest to the atomic propositions. Here it is the negation applied to P and also the negation applied to Q. Starting with the negation applied to P, in the first row, when P is 0, not P is 1. Likewise, P is 0 in the second row, not P is 1. In the third row, we have P is 1 and therefore not P is 0, and the same again in the fourth row. Continuing the first level for the negation applied to Q, in the first row we have Q is 0, so not Q is 1. In the second row we have Q is 1, so not Q is 0, and the same pattern again in the third and fourth rows. Q is 0, not Q1, Q is 1, not Q is 0. Stepping up to the second level of evaluation, we work on the next connective which combines not P with not Q, namely the AND connective. To fill out the column under the AND, we need to take as inputs the columns under the nots, the first level columns. So in this case we're going to get a 1 only in the first row when both of the inputs are 1. In the other 3 rows we get a 0 under the AND because one or other of the first level inputs are 0. In the third and final stage of the truth table evaluation, we'll work on the outermost connective, the negation, which is then applied to the second level result under the AND. In the first row, we have a 1 under the AND, so the result under NOT is 0. In the second row, the value under AND is 0, so the result under NOT is 1. In the third row, the result under AND is 0, so the result under NOT is 1. And likewise in the fourth row, the result under AND is 0, so the result under NOT is 1. This means that for the formula under evaluation, NOT of not P and not Q, we have this pattern 0, 1, 1, 1 going down the column of the truth table where the order is written in standard binary number order. It is false if both P and Q are false, and it's true in all other circumstances. Where have we seen this pattern before? Yes, indeed. This is exactly the same pattern as for disjunction, P or Q, 0, 1, 1, 1 down the column. This relationship of having the same truth table pattern that holds between the formula P or Q and the formula not P and not Q, is what's called logical equivalence. We'll return to this in a few lessons ahead. In the next lesson, we'll get further into the business of semantics and turn to the truth table rules for the harder and trickier connectives, the conditional and the biconditional.